Welcome everyone to our usual Wednesday group seminar. And well, today we delighted to have Dmitry Chicherin from LAPTH from Manisilavia, who will present his work on energy correlators in four-dimensional gravity.
Okay, thank you very much. It's a great pleasure to give this talk at ATMP. So this talk is based on our recent work in collaboration with Grigory Korchemsky, Emery Sakachev, and Alexander Zhiboedov. In this talk we're interested in scattering and gravitation theories. So. Gravitation forces are long range. When we describe scattering in gravitation, we encounter infrared divergences. In particular, scattering amplitudes themselves are infrared divergent, so we cannot use them as observables. We are looking for another class, an interesting class of observables in this theory, and we propose energy correlators as such a class of observables which are infrared-finite in graviton scattering. Energy correlations, they are well known in collider physics, so it's natural observables to calculate in QCD. Recently there have been search of activity for studying them in particular in conformal field theories and in gauge theories, but not so much work has been done in gravity. I'm going to review some basic facts about energy correlations. Also, I'm going to briefly summarize what is well known about infrared behavior of gravitation theories, and then we go to main course. It's what we did in this work. So we considered finite order calculation, namely we considered one loop calculations which probes quantum corrections. It's the lowest order at which we can see quantum corrections and see how these infrared divergences cancel out in calculation of these energy correlations. And another topic, it's about the asymptotics. So there is interesting kinematic regimes in which we can make predictions at finite coupling to the resummations. I can summarize the idea of this talk that we use some well-known collider tools, some calculations in which is usually done in gauge theories to study scattering in gravitation. Okay. We discuss scattering of gravitons, and in gravity the force is long range, and it means that asymptotic dynamics of asymptotic states they are not free; they have non-trivial dynamics. And in particular, it means that non-trivial S matrix doesn't exist for plane waves. In practice, it means that if we try to use Dyson construction of S matrix and do calculations in perturbation theory, then we encounter infrared divergences. There are how we can mitigate this problem? One approach is well known. It was which was pioneered by Fadeev Kulish for massive quantum electrodynamics. It's to consider take into account these non-trivial asymptotic dynamics and to consider dressed S matrices. They are infrared finite. And for gravity, this also was studied not so long time ago. And so gravitational S matrix can be defined taking into account dressing of asymptotic states. At the same time, a lot of things are known about amplitudes, despite the infrared divergent. We can do some calculations can be done. using quantum field theory methods, and there was a lot of activity in this direction. So in particular, there are very efficient calculational tools based on shell techniques such as generalized unitarity, which enabled construction of loop integrants, and also in particular color kinematic duality. Yeah, well, this relation is very helpful in constructing loop integrants of amplitudes. Okay, so now loop integrants in supergravity are known at incredibly high orders, like 5 loops in 4 point for scattering of 4 gravitons. Calculation of these loop integrants is not so advanced, but still there are some interesting results in particularly in supergravity. So like to loop 5 graviton amplitude or 3 loop 4 graviton amplitude, and also some loop results are available for pure gravity. And also these results about amplitudes, they were very useful in studying of classical gravitational scattering. So as information about classical gravitation can be extracted from quantum amplitudes. Okay, so but we are going here to do something different. We don't want to work with these stress test metrics. We want to define some inclusive observables. So in inclusive observables, we sum over all possible final states. And for these observables, we don't need S matrix. We can work with infrared divergences. For example, at calculation at next to leading order, it involves real and virtual corrections. So a virtual correction, it requires loop amplitudes, and in real corrections, we use tree-level amplitudes, but with higher multiplicity. And at next to leading node, there are more contributions. Each of them are infrared divergent, and there are some non-trivial cancellations of infrared divergences between them. But in this talk, will be interested in this analog calculation. It's already sufficient to demonstrate some interesting to show some interesting calculations in gravity and to see how this cancellation of infrared divergences works in practice. So these inclusive observables in gravity have been considered some time ago already, like differential cross-section at next to leading order. But we are going to consider something different in our class of inclusive observables. Namely, we are going to study energy correlations. So our thought experiment is as follows. So here it is a space-time diagram. Here we have a pair of gravitons which collide, and in the collision produced radiations and other gravitons. And we have detectors which are located at time like infinity, which measure energy of this radiation. So more concretely, our detectors are energy flow operators, and they are defined as follows. When each detector is characterized by its direction, and when it acts on plane wave states, it measures energies of asymptotic. It measures energy of particles which propagate in direction of detector. So here we have this delta function on the sphere, which selects only those particles which propagate in the direction of detector. We can depict the same experiment in this way. So we have this n it's direction of colliding gravitons. So here we work in center of mass frame. Their moment is as follows. Okay. And in directions n1, n2, and so on, we have located detectors. So these detectors are at infinity, and this sphere is a celestial sphere. And so what we need to calculate these matrix elements. So here psi it's the initial state of 2 gravitons, and detectors measure energy in the final state of, to which involves this 2 graviton state. Okay, to be more specific, how to let's rewrite this
Can I ask?
expression. Yeah, yeah, sure.
So, like from your previous, yeah, from this picture, I don't quite see how like this resolves the infrared issues because, well, you still have gravitons, right? Which are like incoming.
Yeah, yeah, yes.
But you said that you cannot define them as asymptotic states.
Well, when we consider inclusive observables, um, uh, uh, um, okay, there is non-trivial dynamics of asymptotic states. That it means that we cannot define this matrix, but in principle we can do uh, calculations considering scattering of plane waves. It's not a problem. So in these inclusive observables, at the end we'll see that all infrared divergences cancel out. Um,
So these are not exactly gravitons as they appear in the slide.
so they are not dressed states, it's just plane waves.
But isn't that the place where these divergences occur normally in the usual matrix approach?
Uh, well, divergences, divergences appear when you calculate matrix, well, elements of S matrix elements. But if you sum over all possible final states, then these divergences they go away. So in fact, it's the idea of this talk to demonstrate that how it works in practice, to see that these cancellations they do happen. In actual calculations. So in our words, we want to consider this virtual and real contribution, calculate them explicitly, and see that there are cancellations between them. So
Okay.
their sum is finite.
And okay, and there another like question. So
Mhm.
you also have this well out states, right? And you
Yeah,
say that they reach this null infinity, which means that they are massless as well,
yeah,
right?
the massless. We produce gravitons here. We massless scale. Everything is massless here.
And nevertheless, you don't have those issues, infrared issues.
Sorry, say it again.
And you said that nevertheless you will resolve the infrared issues despite.
Yes, yes, exactly. Yes, well, yeah, yes, exactly. So okay, if I go to the next slide.
Okay, okay, thanks.
Okay, so let's rewrite this.
Excuse me, can I also ask regarding
Yeah.
the same question? Can you summarize what exactly helps to cure the infrared issues? Is it the in-out formalism which is wrong and you use in formalism? Is it that you choose correct these fantastic energy correlators and they cure the infrared issues? What helps?
Okay. So what helps? Okay. So if you want, we're using in formalism. In practice, we use amplitudes. So what I want to calculate weighted cross sections. Okay, so what helps that it's not just a total cross section, we measure energies. So it's important that we measure energies, and this helps to cancel out infrared divergences.
So if I simply calculate the total cross section, the inclusive cross section,
Yeah,
then
yeah,
it will diverge
yeah, yes, yes,
directly.
yes,
It
of
will
course,
directly diverge, but your quantity it doesn't diverge.
yes,
That's the
yes,
thing.
yes.
Okay, thank you.
Mhm. Okay, okay,
So can I also ask,
yeah,
so
yeah.
the usualist matrix, say scattering amplitude, it's covariant under Lorentz transformations if you transform the momenta. So in that sense, this energy correlate, it kind of not Lorentz covariant in the same sense because it does depend on energy explicitly.
Well, it's no, no. We have Lorentz covariance, so this total energy of the process, it's like what P1 plus P2 squared, right? Total energy.
No, and the Lorentz summation, this is zero component of a vector, so it will transform to some other component. No, I think it's frame dependent object, but the amplitude is not invariant; it's covariant. That's true.
Yeah, yeah, yes.
It's the same as here, but what my only point is that it gets transformed not into energy correlate, but into some energy momentum correlate, something like that. Maybe it's just confusing for me. Sorry.
Okay, so well, no. Okay, maybe when I go on, maybe it will be more clear when I discuss in more details. The idea that these detectors, they sit at infinity, and when we do transformations, we we transform these detectors, yes, which sits it's infinity.
Yeah. Okay. Thanks.
Or maybe I'll show formula which clarifies this issue. Okay, so here we have so here this is an expression for these energy correlations in terms of amplitudes. So we take amplitudes, square it, and integrate to our final states, but we weight it with detectors. And also we need to sum over arbitrary number of particles in the final state. Okay, so as I said, so here we are mostly what's important for us is infrared physics. So it's so let's discuss infrared behavior of amplitudes in gravity and more generally of observables. Gravitational observables. So this study of infrared physics and gravity, it dates back to Weinberg, his seminal paper from 1965. So Weinberg he used iconal approximation. So in these approximations, he showed that if we have a amplitude, scattering amplitude with soft graviton, and then these other scattered particles can be massive, and these are not necessarily gravitons. We can be some scalars, fermions, and so on. They can have mass, but gravitons couple to all of them in a universal way, and this coupling is described by this soft factor, which is essentially iconal current contracted with polarization tensor of graviton. And then using these iconal approximations, he also studied real and virtual correction. And virtual corrections, so here he considered ladder and cross ladder diagrams. So here gravitons, they couple to iconal to this iconal current. So it means that emission of individual soft gravitons independent, and in fact these combinatorics just result in exponentiation of one loop correction. These are virtual correction, and in a similar way, real corrections can be taken into account, and then they sum together. All infrared divergences cancel out, and the cross section is described by Bremsstrahlung function, gravitational Bremsstrahlung function, which takes this form. And so it completely controls infrared properties of the scattering. Okay, but analysis of Weinberg was based on iconal approximation, and we know that in gravity is highly nonlinear. There are a lot of interactions, and one could worry that if we take into account other diagrams, and there are plenty of them, that it could spoil analysis based on iconal approximation. But in fact, it holds all those complicated interactions. We only introduce some numerators, kinematic numerators, which help to cancel out, to suppress all divergences. And this analysis was done by Sterman and collaborators. They used tools well known in gauge theories for studying their collinear and soft behavior, So amplitude factorizes in a hard part, then a soft part, and jet. Soft part are just soft functions, some diagrams where momenta are small, and in jet it corresponds to collinear divergences where all momenta are collinear. And by doing some power counting of momenta and using word identities for gravitation, they show that there are no collinear divergences. So it's very different. So gravity is very different as compared to gauge theory, where we do have collinear divergences. Then soft divergences, then they appear only in these ladder and cross-ladder diagrams of this type, where soft graviton is attached to a line with finite momentum. In other words, more complicated diagrams where there are interactions of several gravitons, they are suppressed and they don't contribute to divergence. Okay, now let's discuss, since we are going to consider energy correlators, or correlators as you wish. So let's discuss them in gauge theory, so review some basic facts about them. So these energy correlators, they are well known in collider physics. So they help to study dynamics of quantum thermodynamics and to implement some precision test of standard model. In particular, they are used to measure strong coupling. They are interested in hadron colliders as well as lepton colliders. So these are natural language for studying jets and to study substructure of jets. So let's consider them in the setting of lepton collider, where we have electron-positron annihilation. So in this annihilation, virtual photon is produced, which is off shell, and then it decays in a pair in quark-antiquark pair, which is dressed by gluons and also quark-antiquark pairs, which go through fragmentation, and they hadronize, and at the end there are some jets which go into detectors and are measured. So in this case, correlation between two detectors is defined as follows. So it's essentially the same as definition as before, but here we consider it in a decay, where there is a massive state which decays. So here we sum over all pairs of final state particles, and we weight them with energy, and insert this delta function, which picks those pairs of particles for which this angular separation theta, what should be angle theta here, so that this angular separation of two particles is the same as angular separation of detectors. So this observable has been introduced in 1978 in this way in QCD, and at leading order it has a very simple form like this. So this is expression in QCD, and on this plot you can see this leading order expression. It is plotted here. So it has it has singularities at here you put variable z, which is just it varies between 0 and 1, and it's just angular variables. It's the same as angle. Well, it's just convenient to use it. So at the opposite ends here, here z equals 0, it means that two detectors are collinear, and z equals 1, it means that detectors are oriented back to back. So they have opposite direction. We can say that back to back or anti-collinear. So in these regions, the singularity originates from soft and collinear divergences of in gauge theories. Well, in our interest in observation is that these energy correlators in gauge theories, they can be reformulated in completely different way without using amplitudes. Namely, we can construct detectors out of local operators. So let's take stress tensor just stress tensor. We use stress tensor operator and put it light like infinity and integrate. Yes, we put in light like infinity in the direction n. So n is the direction which specifies it, just a vector on two-dimensional sphere which specifies directions of orientation of our detector. So we put our detector at infinity and integrate over retarded time so that its detector is turned on during infinite time. So this blue line is where our detector sits. So we see that detector is formulated completely in terms of a local operator stress tensor. How does it help? Using this, we can reformulate this energy correlator in this form, right, as a correlation function. So O here, operator O is just source. It acts on a vacuum and creates a massive state. Well, if we are talking about this electron positron annihilation, this O should be a electronegative current. But let's keep just some generic operator, any operator. And so this state is created, then it's measured by detectors, and it propagates back into the sink. So how to see that this amplitude formulation and correlator formulation are related? We just need to insert in this correlator a complete set of states, so it's calculation like optical theorem. Here we need to sum over amplitudes of arbitrary multiplicity, but here everything is is taken into account by correlation function. There is no summation here. Then if we substitute here this definition of detector, so we see that this energy correlator is expressed in terms of correlation function of local operators. So in particular, well, it's not so direct that we need to do something with correlation function, but starting point is correlation function. If we have correlation function, we can do something with it. Some operation at the end, we should get energy correlator. So in particular, it means that energy correlator can be introduced in a theory where they have correlation functions, and the correlation functions natural language for conformal field theories. And in this case, we don't have to worry about asymptotic states. If we have correlation function, we can start thinking about energy correlators or correlators of our detectors, which can measure something else. This was very fruitful approach, and it attracted a lot huge attention of community of people working on conformal field theories. It also was helpful in practice for doing calculation. For example, it enabled calculation at next to leading order and next to leading order in maximal super young Mills theory, which is not doable by amplitudes. It would be very complicated to do calculation of this. And also this representation is helpful for studying asymptotics in singular kinematic regimes. For example, when a pair of detectors become collinear, and it's interesting not only in conformal field theories but also in QCD. So even in QCD, it's not so easy to calculate correlation functions, but this representation itself is a good starting point to start to use some OP expansion and to try to do resummations using these ideas. Okay, so previously there was question about Lorentz covariance of detectors. So here maybe this picture helps to understand better Lorentz covariance. So detectors, it sits at this time like infinity, and it's integrated over retarded time. So this is what this detector. So it should explain its Lorentz covariance. Okay, so then what I want to say that energy correlators, there is growing interest in this kind of observables, so they are relevant for particle physics in practice for doing phenomenology. they also related to conformal field theory because of these correlation functions. And also we could need amplitudes to calculate them. So energy correlators are interesting observable which sits between amplitudes correlation functions. And also it's interesting to start to study in gravity. There was a lot of activity in on this side, but in gravity they're not so well studied, and this is what we are going to look at now. So maybe before proceeding directly to gravity, maybe it's well, I should compare the energy correlators in gauge theory and gravity. So this setting, what's the difference between them? So as we discussed in gauge theory, if we are thinking about electron-positron annihilation, and with annihilation a massive state is produced which decays. So to calculate energy correlators, we could use form factor of operator. But in the gravity case, we don't have massive state. We always have initial state radiation because gravitons, they universally couple with everything, and so we have to use we have to start with we have to use amplitudes where we have collision of two gravitons. Also, in case of gauge theories, there are formulations in terms of these amplitudes of form factors, and also formulation in terms of correlation functions of local operators. But in gravity, we don't have local operators because of general covariance. We cannot work with operators. We cannot formulate them local operators. So we have to rely on amplitudes to calculate energy correlations. Okay, so this is just setting how to define these observables, but also their behavior is qualitatively different. So in particular, as we discussed in gravity, there are no collinear divergences, and in gauge theory there are collinear divergences, and in particular it means that behavior of these energy correlations is different in the case then detectors are collinear. We are going to discuss it in more details, but it's just to say that because of different infrared physics in two theories, in these observables, they have different behavior. Well, okay, so before proceeding to our work, I should mention this beautiful work, which reviews a lot of ideas about energy correlation and energy correlators in conformal field theories, and it also uses both language of conformal field theories and the colliders, and also offers the study also scattering in gravity using energy correlations, but we are going to study gravitons, but they scatter scalars. And what we do, calculations which we do, it is based on tree-level amplitudes. So it's essentially, well, tree-level calculations in some sense. So they cannot probe infrared divergences. But we are going to do something different. We are going to probe quantum effects to see how infrared divergences appear in these calculations and how they cancel out. Okay, so so let's discuss calculation of energy correlators at leading node, at next to leading node, and we'll focus on two cases when we have one detector and the case when we have two detectors. And so we skate a pair of gravitons, and we measure these detectors radiation at infinity. Okay, so this, well, first of all, what is the geometry of this third experiment? We work in center of mass frame. So we have this direction n. It's let's call it direction of a beam, a direction along which gravitons collide. And also we have several detectors. If we have one detector, let's denote it n1. So in this case, we have only one angular variable. Let's denote it y. So here, and y changes between 0 and 1. If we have two detectors, then we have more directions. We have this beam direction of collision of two gravitons, but we have also two detectors, and directions n1 and n2. So we have three angles which characterize these kinematics. Angle, well, we use variable z, which varies between 0 and 1 to specify angle between two detectors, and also variables y1 and y2. It's angle between beam direction and detector. The detector n1, detector n2. So one variable here in the case of one detector, and three variables in the case of two detectors. Okay, which theories we are going to consider? So, well, first of all, it's maximal supergravity. Why maximal supergravity? Well, it's a good testing ground for doing perturbative quantum gravity calculations because amplitudes in this theory are particularly simple, and this theory has improved the UV behavior, so we don't have to worry about ultraviolet divergences. And so in this case, I should mention that okay, there are we scatter not only gravitons, but we can consider scattering of all the superpartners, and there are 256 on-shell helicity state in this multiplet, and we can consider scattering any of them. But for our NLO calculations, we also do calculations in pure gravity. We don't have problems with ultraviolet divergences at this order because amplitudes, this graviton scattering at one loop is ultraviolet finite, so no problems with ultraviolet divergences. And so there are no much difference between supergravity and just pure gravity for these calculations, because we are mainly worried about infrared physics, and infrared physics is the same in both theories. In case of supergravity, expressions are just more compact and more presentable, but there are no big conceptual differences. And also for some observables, for some calculations, we can also take into account string corrections for supergravity. Okay, so let's start with one detector case and calculation and do calculations at leading order.
So,
yeah.
Quick question. So, for all these calculations, you basically need only 4-point scattering amplitudes, right?
No. If we consider leading order, then it's indeed 4-point amplitudes. But if we consider next to leading order, which is the most interesting thing, where we can see infrared physics, there we need 5-point amplitudes.
Okay.
Three-level 5-point amplitudes.
Excuse me, can I ask about whether they are ultraviolet finite? I didn't understand. In supergravity, of course, there is a cancellation, but in pure gravity, you will calculate eventually in pure gravity.
It's just one loop. It's just at one loop.
It's at one loop.
Yeah, but what about fish diagram? Just maybe a stupid question. Just a fish diagram, which is like graviton to the cube vertex, two vertices of graviton to the cube, just the most trivial loop. Is it finite?
Well, one loop amplitudes in pure gravity, they don't have ultraviolet problems, so they only have soft infrared divergences.
It's only one shell. One shell.
Oh, it's on shell. Yeah,
okay.
it's on shell.
Okay.
Everything amplitudes. Yeah.
You do not consider corrections to the propagators, right? They cancel kind of on shell. They can.
Well, if you mean that there are green functions, we don't consider green functions. Yes, we consider amplitudes, and on shell at one loop there are no problems. So these counter terms, they go away.
Okay. Mm-hmm. Thank you.
Okay, so Okay, so it's one detector case and leading order calculation. Okay, so for this, what we need to do, we need to take tree-level amplitudes for point 2 amplitude, square it, sum over all final states, and integrate. So what we need matrix element that amplitude squared and summed over final state. So this is so gravity amplitude. It has poles in what usually call STU channels, and they appear in the denominator, and the summation of a multiplet, supergravity multiplet, it gives this simple numerator. It's also interesting that in case of supergravity, we don't have to specify helicity of initial state. So it's due to supersymmetry. It turns out that this matrix element is the same for any initial state. So we can take pale gravitons of any helicity, and or their super partners like scalar fermions. Matrix element is always the same. So now what's this helicity state of this particle P1, P2 can be, well, anything from the supermultiplet. So we sum only over states, final states, helicities of the final states. Okay, so this calculation is just trivial. Let's take this matrix element squared, and space-time, sorry, integrations of phase space is trivial. Why they are trivial? Because kinematics is completely fixed. So our detector inserted here, it fixes scattering angle. So it is direction between incoming gravitons and outgoing pair of gravitons. So the directions is incoming n and outgoing direction n1, and this is angle which is fixed. So answer is very simple, and it has poles at y is angular variable, and these poles, it's poles of forward scattering, and this is exactly poles which result in divergence in total cross sections, and gravity. Just well, okay. So
Sorry, can I ask something?
Yeah.
So do you understand correctly that this cross, it means that, well, you have this like some sort of like component of stress energy tensor, which is bilinear in fields, and that's why it has two lines. So
so here we use amplitude. So when I was talking about stress tensor, it was for gauge theories where we can define stress tensor. Here we don't have local operators, and here we just measure energy. So this cross, it means detector. In practice, it means that I here measure energy of this particle Q1, that is its energy, it equals E, right? And also detector selects particles which have momenta aligned with detector. So detector selects particle, it imposes that momenta of this particle is oriented in direction n1. N1, it's direction of detector. Detector detects only particles which flow inside detector, and the particles which well, fly away it doesn't detect it. Yeah? So detector selects only those gravitons, final state gravitons, which fly, which are with moment oriented in the direction of detector.
Okay, but other than that, these are just usual Feynman diagrams for amplitudes.
Yes. So well, amplitudes are well known. We don't need to recalculate them. We just take these tree-level amplitudes 2, take its square, sum of final state, and answer is very simple. This is just these matrix elements squared written in detector variables. We just need to replace momenta by the expression in terms of the direction of a beam and direction of detector.
Mm-hmm. Thank you.
Mm-hmm. Okay, so what about case of two detectors, also at leading order? Well, here we have two possibilities. We can put detectors, we have two detectors, and we can put them on two different lines, two different final states, or we can put both detectors on the same line. So here it means that the detector, one particle, both detectors measure the same particle, the same energy. Okay, and this is only possible if detectors are collinear. They are oriented in a collinear way, like on this picture. Right? Because they measure, direction of detector is aligned with particle which it measures, and if both detectors measure the same particle, both detectors have to be aligned. This variable z is angular separation between detectors, and z equals 0 means that they're collinear. Well, if these two detectors are on two different lines, then it means that detectors have to be anti-collinear or back to back. They have opposite direction. In our terms of our variables z, z equals 1. So in the previous case of one detector case, kinematic was already constrained, but here kinematic is over constrained, and it means that expression for this energy correlator is just contact term. Sum of two contact terms, collinear contact term and back-to-back contact term. So here maybe my terminology is not standard. So if we are naive, we would just omit these contact terms and say that okay, it is 0, and we don't consider it as a leading order, because leading order is something which is first non-zero result. But okay, I want to that my counting of orders is aligned for one detector case and two detector case. So let me call it also leading order. Okay, why these contact terms are important? They are important because of energy momentum conservation. If we take endpoint energy correlator and integrate over all possible orientations of one of the detectors, it means that we measure total energy. And so doing this averaging, we should get total energy, which is in our notation it is 2E times correlator where this detector is taken away. So in particular, in this way, we can go from two detector case to one detector case by integrating out one of the detectors. Well, a similar situation for momentum, for space momentum. So if we average multiplying by this vector, so we should get 0. In other words, we measure total momentum, total space momentum, it should be 0. So, and you see, if here we naively said that 2-point correlator is 0, then in averaging it, we also get 0, and we cannot get a non-trivial 1-point correlator. So this relation, energy momentum conservation, holds only because of contact term at leading order. Okay, let's proceed to indeed non-trivial calculation. So one detector case and next to leading order calculation. So here we have virtual contribution and real contribution. Virtual contribution, it uses one loop amplitude and one loop amplitude times 3-level amplitude. And in real contribution, we have a product of just square of 3-level amplitude 2 to 3 scattering. Both these terms, they have infrared divergences. Infrared divergence of virtual correction, it comes from soft divergence, soft pole of one loop amplitude. So, and the integration here is trivial. It's like what we discussed here at leading order, like where we have just elastic scattering. So kinematics is completely fixed. So, and the divergence, this pole, it is soft correction of one loop amplitude. But here, amplitudes finite, just 3-level expression, and divergences, they originate from integrating over, and they originate from phase space integration, and they are related to this undetected soft radiation. Doing calculations, well, we can see that divergences match each other. So this simple pole in dimensional regularization. Here in virtual correction cancel out exactly also simple pole in from the real correction. And the final expression is very simple. Well, it's very nice. In particular, in supergravity, it has uniform transcendentality. Okay, let me plot it. So here, so here it is plotted for supergravity, but also for pure gravity. In pure gravity, I have to specify polarization of initial state. So we can have, we can consider a collision of two gravitons which have the same polarization, opposite polarization. Answers are slightly different in two cases. And in supergravity, there is no dependence on polarization of initial state. It's a consequence of supersymmetry.
Can I ask the following question? How do you get the gravity answer? Do you just take a supergravity and kind of calculate all fermionic diagrams, whatever, or you calculate from the get-go, from the scratch?
No, amplitudes are well known. In fact, if we are talking about three-level amplitudes, then we can take, well, a supergravity expression. We just need to sum over a different set of final states. Well, if we had three-level amplitudes are just exactly the same. You take in supergravity amplitudes, we can extract immediately, well, from them component corresponding to graviton scattering, right? And for one loop amplitude, this to scattering, its amplitude is also well, it's well known. It's well, it's given by essentially at one loop. It's just a zero mass box integral sum.
Yeah, can I reformulate the question like this? Does supergravity help somehow to calculate amplitudes in gravity? Probably the answer is no.
One loop, okay. So, for this calculation, in fact, amplitudes are well known, and we extracted them from papers of papers of Bern, Bern, and from 90s, and these are well-known expressions. If they, how they were calculated, so here they relied on generalized unitarity, I think, to do this kind of calculations. Not so instead of using Feynman diagrams, they relied on this generalized unitarity. At one loop, it works in a very simple way.
But they do look. I think they look. The expression looks simpler than gravity. I think the final part, right?
Yes. In supergravity expressions are simpler. If we are talking about loop amplitude, loop amplitude in supergravity, just a sum of zero mass box in various orientations, which respects this full crossing symmetry. And in Einstein gravity, there are also some rational contributions and I think some log square terms, but it's also well. At these orders, expression for amplitudes, they don't pose any problem. All these expressions are well known. They were calculated a long time ago, so we can recycle this data.
Okay, thank you.
Okay. Okay. So what? Okay. So so far we discussed energy correlators. Our detectors measure energy, but we can also consider measuring higher powers of energy. And in this case, it turns out that also there are cancellation of infrared divergences. So we can consider detectors which measure not energy but higher powers of energy. It's also fine. Okay, so then case of two detectors here. Well, situation is more interesting. So it's we have two detectors at next to leading order. In this case, so we have real and virtual correction, and we also can distribute our detectors in several ways. We can put them on the same line, like here and here, or on different lines. So let's discuss each of these contributions separately. So when, okay, so first of all, case when we put both detectors on the same line. Here, well, if we look at expression of detectors, we immediately see that it can work only if detectors are collinear. It's like what we discussed previously. Both detectors measure the same particles, so they have to be aligned, they have to be collinear. So this contribution is just contact term, and the calculation is essentially the same as previously in one detector case, but we need to measure not energy, but energy squared. So here my notations a little bit sloppy. I don't take square of detector, it's just detector which measures square of energy. But the calculations is well, go in the same way, and okay, we find so the reconciliation between virtual and real infrared divergences in real and virtual contributions. Okay, and we find this correction. What is interesting here that we expect that these okay, what I want to say, okay, so we have a contact term, but there are no collinear divergences in gravity. So other contributions in this collinear regime, they should be regular. So this contact term is it's the leading contribution. And so we expect that also at finite coupling, this OP of two detectors should take this form. So there is contact contribution from detector which measures square of energy, and our contributions they are not singular. So this is difference with gauge theories. In gauge theories, there are collinear divergences, and the collinear divergences they modify these delta functions so that they are some in some power dependence, power scaling in the collinear regime. Okay, so another contribution in energy correlation at next to leading order, it's real contribution 2 to 3. So to calculate it, we just need to take tree-level amplitude squared and integrate over this final state and insert into detectors in different lines. And these two detectors, we simplify a lot this phase space integration. So at the end, it's just a one-fold integral. And this can be easily calculated, and well, what we find just some function of free variables. Well, if we plot it, so here we fix, well, here it means that we somehow plot y1, y2, and consider as a function of z. So at z equals 0, as I said previously, it is finite because there are no collinear divergences in gravity, but on the opposite end, it has a singularity. It's related to soft physics. Okay, but the question is why this finite? So this is real contribution, and we expect infrared divergences in this real contribution. And where are they? Why we don't have to cancel them? And where are contact terms? And to see what happens with infrared divergences, we have to remember that there are also virtual contribution where we put detectors on opposite line. So this is contact, as we discussed previously. These detectors have to be back to back because elastic is this is elastic scattering. Detectors have to be oriented in opposite way, back to back. And this contact term, it's not only contact term, but it also has divergence. It has this soft divergence of one loop amplitude. And doing analysis of this real contribution, accurately, well, keeping in mind that it's in fact not a function but a distribution, we see that it's asymptotic at z equal 1. It contains exactly the same delta function, which also has this in this infrared pole, and these two infrared pole cancel each other. Residue at this pole, it is related to cusp gravitational cusp plate-like anomalous dimension. Well, I don't know if I have time to discuss it, but okay, point is that there are cancellation. So the final result is finite. So and there are cancellation so infrared divergences in both contact term, in a collinear contact term and back-to-back contact term, and so if we are not accurate and we forget about contact terms, then we would forget only this contribution, some regular function of free angles, and we would miss this contact term. But we remember that they are needed if we want to verify energy momentum conservation. So to go from 2-point correlation function to 1-point correlation for two detector case to one detector case. Okay, so why these contact terms are interesting? We already discussed collinear contact term, we believe that this contact term is describe this collinear OP. But back-to-back contact term, it's an artifact of perturbation theory. It appears at each other in perturbation theory, but if we do resummation, we expect that it, in fact, we can see that it goes away if we do resummation. How it works in practice? Well, expression at finite coupling takes this form. So here, this it's coupling, gravitational coupling. If we expand in this gravitational coupling, we will get singularity 1 over 1 minus z enhanced by large logarithm, log of 1 minus z. And but also, if we do this expansion accurately, keeping in mind that it's distribution, then we also extract these contact terms, which we see in perturbation theory. Okay, so what can also we do it next to leading order? So let's forget about contact terms. Previously I said that they're important, but okay, let's forget about them. I use only 3-level amplitudes and average over the orientation of a beam. So before averaging, we have a function of free angles. It's difficult to look at it. It's a little bit bulky expression, but if we average all of this direction, then we keep only dependence on the angle separation of two detectors. So in some way we project it and keep into account dependence only on the one variable. And we find that it has very simple expression, very simple, nice expression, which if we plot it, it is very reminiscent of what we saw in gauge theory. There also was a plot like this, which is flat in the middle and which has singularities on the opposite end. A singularity at z equal 1, that is back to back, it corresponds to soft physics, soft divergences of amplitudes. But behavior here, it is not collinear divergence. It's somehow related to forward scattering, because when we integrate over possible orientations of a beam, we have to probe region where detectors are. This direction, when we average over beam direction, it goes through the region or through the direction of detectors, and so the singularity is the same as forward scattering singularity of amplitudes, of gravity amplitudes. Okay, so the same observable can also be easy to calculate in string theory, take into account string reactions. So here we only consider low energy limit of string theory, where we in the final state we consider only massless final states, the same as in supergravity. So all string effects, they appear in the modified interactions. Okay, we can do these calculations, and okay, just somehow picture which illustrates it, and okay, maybe to say that stringy corrections, they are suppressed as compared to supergravity. Okay, so I don't know if I have time. What I wanted to say briefly, some words about order resummation. So previously we considered calculation of fixed order next to leading order, but some more can be said in the case where two detectors have opposite orientation. Yeah, okay. Why it's the case? Because in this case, this observable is dominated by soft physics. Namely, if our detectors are oriented oppositely, they detect two particles, two hard particles, which essentially carry the most of the total momentum, and what remains it is carried by soft gravitons, which are undetected. So what we need to do, we need to integrate out these soft gravitons. So to specify this, to describe these asymptotics, it's convenient to introduce this vector L perpendicular, which is a two-dimensional vector, Euclidean vector, small, just a sum of these two n1 and 2. And in back-to-back limit, these vectors n1 and 2, they are almost, well, opposite. Their sum is almost zero, so this L perpendicular is small. And this vector squared is just 1 minus z, and z is our variable which goes to 1 in back-to-back limit. So in other words, what we need to study these asymptotics of this observable when this vector L perpendicular becomes small. Well, in terms of amplitudes, it's this picture. So there are among final state particles, two take most of the momentum, and we only need to integrate out of this soft radiation. And this soft radiation, it is space-like, and it's a direction given by this vector L perpendicular. Okay. Why it's possible to do? Well, it's essentially based on the Weinberg analysis, which we discussed previously. So Weinberg showed that there are exponentiation, there is factorization of hard and soft corrections, and soft corrections, they exponentiate. So all these soft corrections, soft gravitons, they couple with acanal current, and we can represent them as this time moderate exponent. So acanal current coupled with soft gravitons. Okay, we have already considered virtual corrections. So namely, if we take this vacuum expectation value of this T exponent, we essentially what we just stretch soft graviton propagators between pairs of lines with finite carrying finite momentum, and we already discussed that it's well, it's just exponentiation. Exponentiation of one loop correction. So here we have a graviton stretched between two acanal currents. So calculating it and exponentiating, we find all virtual corrections, all virtual soft corrections. Okay, I should speed up a little bit. Okay, how this looks like if we do calculations when we get very simple expression, which is well known. And we get this double pole, but in fact, if we expand in epsilon, we see that double pole goes away because of energy momentum conservation, and so what remains only simple pole, and it means that the gravity amplitudes they have only soft divergences, they don't have collinear divergences. It's worth comparing with the same calculation in gauge theory. So if we stretch if we stretch a gluon between two well, acanal propagators, do a calculation, then instead of Sij, modest variable, here we have color operators, and expanding in epsilon, we see double pole, which correspond to soft and collinear divergences, and residue with pole, it is Casimir operator of color group, and and in fact it gives cusp-like anomalous dimension and gauge theory at one loop. But in gravity, everything these divergences are much simpler. There are no collinear divergences, only soft divergences, and they are described by these gravitational cusp-like anomalies, which is a loop, which at one loop is exact because of this exponentiation of divergences. So at two loops, all divergences are specified by this cusp anomalous dimension. There are no two-loop corrections and so on. Everything is simple and exponentiates. So what we need to do, so we to calculate energy correlation in this back-to-back asymptotics, we just replace amplitudes by the factorized expression where we have hard part and the soft part. And what we need to do, we need just to integrate out this soft radiation. As we said, this soft radiation, it's momentum in orthogonal direction, it is, well, it's fixed by geometry of our experiment with L perpendicular, this small two-dimensional vector, which is vanished in this back-to-back limit. Again, so this calculation is very simple because of exponentiation of infrared or exponentiation of virtual and real corrections. So by doing a small trick, we can rewrite it in this way, where this function f, its function is in space-time, but one loop. And so it is, and it contains real corrections, which is given by this cut propagator, and also virtual correction and its conjugate. So essentially, this exponentiation of this one loop function, it results into this more complicated picture where we have multiple graviton corrections and exchanges, but it's just in fact one loop exponentiated. Okay, so this function, in fact, it's infrared-finite because of cancellation between real and virtual corrections. And to calculate, well, in principle, it's possible to calculate this function, but to extract asymptotics, we don't need to know full expression for this function. We need only to know how it scales the length of this vector x perpendicular, which is conjugate to the this L perpendicular, which governs the asymptotics. Okay, this calculation can be done well using ideas from renormalization, ultraviolet renormalization group, and it turns out that this behavior of this function, it is controlled by also this Caspar anomalous dimension. Well, I'll omit this calculation. It's very simple. It's very simple calculation, but it gives this very nice formula, which says how this energy correlator, how it behaves in this back-to-back limit. So when these detectors are opposite. So as so what we achieved here, we summed all large logarithms in well, at high orders of perturbation theory. As we can see, there are no contact terms. So these contact terms, delta 1 minus ZV, are artifacts of perturbation theory, but in the fine coupling expression, well, it just, well, power 1 minus Z, power 5 minus Z is corrected by Cusp-like anomalous dimension. And also nice feature that this Cusp-like anomalous dimension is positive, so it means it's good because when we if you want to verify energy momentum conservation, we have to integrate over directions of one of the detectors, and we have to probe region where z equals 1. And this integration it's finite in the vicinity of z equal 1. So it's good, so it's reasonable, so it's a sanity check. So function C here, of course we cannot extract it by considering these asymptotics, but in principle it can be, we can find it by comparing with finite order calculation. So for example, our leading order next to leading order calculation, well, it's sufficient to break predictions at two orders for expansion of this C in this gravitational coupling. So in other words, this calculation is very similar to what is usually done in collider physics. There is some where we in singular regimes large logarithms are resummed, and then there is a match in the finite order calculation. So I'm ready to finish, to summarize. So we considered energy correlation with energy correlations in case of one detector and two detectors with paid attention to infrared divergences, and we demonstrated per cancellation between them, and we saw that it's very important to keep track of contact curve because they are responsible for energy momentum conservation. And also we considered resummation of large logarithms in back-to-back asymptotics and derived this asymptotic expression for energy correlation, and we have seen that it is driven by this gravitational cusp like anomalous dimension. Okay, thank you, and sorry for taking more time than expected.
Okay, so let's thank Dmitry. Questions? Okay. Yeah, I believe most of the questions were asked during the talk.
Do you see any contact on perturbative calculations with the CFT on a celestial sphere or something like that?
Oh, I haven't thought about it.
You kind of calculate the correlators of energy on kind of celestial sphere, right?
Yes. Okay. So there are also some works well several years ago. I don't know, maybe here in this review paper there are some reference where in those works people considered a relation of these energy correlators with these BMS symmetry, so they considered correlators of asymptotic charges, and they studied their operator algebra.
Yeah, but basically I see that the answer is basically no, because you don't need this CFT data, just they do not simplify your life, right?
Yes, well, let's say it's a different question. So in principle, you can think about these asymptotic charges and try to calculate their correlators and to study their algebra. In those papers, I think it was done at with semi-classical level, so there was no correlations at all. So they considered some just they haven't probed any quantum effects. But I think that okay, this. To have a better understanding if there is some operators formulation of this is also interesting. We don't have local operators, but we can think about operators which sit at light-like infinity and study the operators. It's something was done in this direction in this paper.
Okay, thank you.
Okay. No questions 1. No questions 2. No questions 3. Solid. Okay. Well, let's thank Dmitry again. Okay, and we see each other next Wednesday on the next ITP seminar. Okay. Dmitry, thanks again for your talk.
Thank you.
Okay.